Tonight, I'd like to welcome Dr. Anke Arden-Arentsen, an observational astronomer interested in the history of the Milky Way and the first stars. One of her areas of work is the pristine inner galaxy survey, PIGS, basically, using telescopes on Hawaii and spectroscopy to survey the properties of metal-poor stars towards the centre of the galaxy. And I believe they've catalogued over 13,000 such stars at the present. In 2016, she obtained a bachelor's and master's degree from the University of Groningen in the Netherlands. And then in 2020, completed a PhD at the Leibniz Institute for Astrophysics in Potsdam, Germany. She obtained a postdoc appointment at the Observatoire Astronomique de Strasbourg in France from 2020 to 2022, and then since October 2022, she's been a Herschel Smith Fellow at the Institute of Astronomy, Cambridge, and a non-stipendiary research fellow at Fitzwilliam College, Cambridge. So please, can you put your hands together and welcome tonight's speaker. Thank you.
Thank you for the introduction. Can you all see my screen all right?
Yes, we can.
Excellent. Okay, let me move this a little bit out of the way. Okay, well, thank you very much for having me with you tonight, and thank you for letting me do this remotely as well. Tonight, we're going to be talking about galactic archaeology with the oldest stars in the Milky Way. So this is actually the title of my PhD thesis as well, and this is work I've continued to develop over the years. So I'll give a very broad introduction, hopefully, and then go into a bit of recent results. So the main star of the show is the Milky Way galaxy. And unfortunately, in many places in the UK, I think you can't really see it this nicely or even at all. But it's this band across the sky that is especially beautiful in the southern hemisphere, where you can see it right overhead. But what is the Milky Way? So the Milky Way is a galaxy among many other galaxies, and this is an artist's impression of the Milky Way. As you probably know, it's not possible to get out of the Milky Way and take an actual picture of it. So we have to do with artist impressions. So you can see these beautiful spiral arms, and we are around 2/3 towards the edge of the disk of the Milky Way. So the distance to the galactic center is around 26,000 light years. So the light takes around this time to travel from the center to us. The galaxy contains around 200 billion stars. So the sun is one of these 200 billion stars. And a mission that has really changed this research area is the Gaia mission. So the Gaia mission has been measuring the positions and brightnesses and colors of stars over the past 10 years or so. And this is on the right-hand side is a map of the stars in Gaia, which is around 2 billion stars. So we have this kind of disk galaxy with spiral arms and all kinds of structure. And very, very simplified, we can look at the structure of the Milky Way like this on the left-hand side. You have this kind of thin disk, which appears as the stripe on the sky, with a thicker part in the center. And this is around 99% of the stars in the Milky Way. But then there's also a halo of stars that's spheroidal, with the highest density in the center and becoming less and less dense the further out you go. But it's not just flat; it's everywhere surrounding. So one of my main research questions, and a big question in the field of galactic archaeology, is how did the Milky Way form? How do we get this structure? And then you can kind of generalize it to how do galaxies in general form, like other galaxies that we see in the universe. So we got to go back to the very start of the universe to where the picture of galaxy formation begins. So at the beginning of the universe, there was a beginning to the universe. That is not actually an obvious statement, and it was first predicted by the Belgian priest Georges Lemaitre in 1931. And from this beginning point, you get a very rapidly expanding universe that is filled with gas. And then there's no galaxies yet, there's no stars yet. So at some way you have to start forming the first structures. And then you get all of this history, is 13.7 billion years of history until the present day, in which all of this happens. You grow from nothing to the beautiful galaxies that we see today. So how does that begin? So here, at some point, you get the very first stars forming. So you have a dark period where there's nothing that is shining. And then you have this age of a few 100 million years after the Big Bang, where you get the very first stars that are starting to shine. And then from that, they start forming groups. The groups start merging together, and you get bigger and bigger galaxies until you get galaxies like the Milky Way at the present day. So here's a little video of a simulation of galaxies forming. So we start back in the past and go forward in time. And you can see this process of smaller things growing, merging together, building a larger galaxy over the course of its history. And at some point, you'll start seeing this disk appearing. I'll zoom forward a little bit. So here you start seeing kind of spiral arms. It's becoming more of a flattened structure. But there's still things that are coming in that are getting disrupted and that are contributing to this growing galaxy. So this is kind of the standard picture that we have of how galaxies and how we think that the Milky Way has formed. So schematically, in the early universe, you get small galaxies. And at some point, you get something that looks a little bit like the Milky Way, and it keeps growing and growing and growing over time, with still new galaxies being added to it as well. So something I'm interested in is to figure out what were the first galactic building blocks. So what were the first things that started forming the Milky Way, and how did this early phase happen? Yeah, so kind of the early ancestry, the baby phase of the Milky Way. So how can we study early galaxy formation, this first phase? So one thing we can do that is in the news a lot recently is you can look directly to the distant universe and see galaxies as they were young. So this is something that the James Webb Space Telescope has been doing. This is a beautiful picture from JWST, and some of these little red dots that, depending on the projector, you might or may not see. These are all very young galaxies that are we see them as they were 11, 12, 13 billion years ago. So you can study this because the speed of light has a finite speed. That means that the further you look, you're looking further back in time. But as you can see, these galaxies are just a few pixels on this image. So there's only so much information that you can get out of these galaxies. We're learning a lot, but a very complementary way of studying this is by looking at the oldest stars in our own galaxy in the Milky Way. And this is what we call galactic archaeology. We're digging inside the Milky Way to find these very old stars, and we're trying to use what are they made of, how are they moving, to learn something about how our galaxy formed. So this is the part that I will focus on in this talk. So going back a few steps, can we even do this? Can we find stars that are very old? So the universe is around 13.7 billion years old. And here is just a schematic of different kinds of stars that exist in the universe, from very red small stars to very hot, big stars. And these are the typical lifetimes for these kind of stars. So these very hot, big stars, they only live for, let's say, 10 million years. So compared to the age of the universe, that's not very long. So if these big stars formed just after the Big Bang, they would no longer be around in the present day. But then the smaller the stars are, the longer they can live for. So if you get to the sun is a G star, like this one, it's a maximum age of around 9-10 billion years. So there's still a bit of a gap compared to the age of the universe. But these really small ones down here, they can live for over 200 billions of years. So if they were formed early on, they would still be alive. They would still be happily doing nuclear fusion in their cores, which is the thing that gives energy and it allows the stars to shine for a long period of time. So for galactic archaeology, the stars that we're interested in are these very small ones that if they formed at the start of the universe, they would still be alive today, and we can see them and kind of use them as a fingerprint of the early universe. So then we're going to get a little bit more practical. How can we recognize these ancient stars? How can we find them and then use them for our questions? So for that, we need to know a little bit about the chemical composition of the universe, what the universe is made of. So in the very early universe, just after the Big Bang, before any other stars formed, we just have a very simple periodic table. So the periodic table is hydrogen, helium, and lithium, and that's it. So the relative frequency is mostly hydrogen, about a quarter helium, and a tiny bit of lithium. And there's no other complexity in terms of elemental presence at this time. But then over time in the universe, over the course of history of these 13.7 billion years, you get all kinds of different processes taking place, like stars exploding as supernovae. You have low mass stars that are dying. You have exploding white dwarfs and neutron stars. I'm not going to go into that for this talk, just to give you an idea of all the different processes that can make the elements. And then here's the rest of the periodic table. And it's color-coded maybe differently than you're used to. Here it's color-coded by where every element is formed, in what kind of process. So here, for example, carbon is mostly formed in dying low-mass stars. Iron is mostly in exploding white dwarfs. And then these elements up here that are probably forming in neutron stars, two very, very heavy remnants of heavy stars that are merging together. So all of this is building up over time. Every time you have a new generation of stars and they explode, this material comes back into the universe, and the next generation of stars can form from this. So that means that after the Big Bang, we have this very simple periodic table, simple composition. So what is the composition of stars at the present day? It actually doesn't look very different, but it is wildly different. So it's still mostly hydrogen and helium, but there's this 1.1 or 2% of metals. And in astronomy, we call everything a metal that's heavier than helium. And this was first realized by Cecilia Payne in her groundbreaking PhD work published in 1925, that stars are mostly made of hydrogen and helium and just a little bit of heavier elements. And although this percentage might not seem very much, we can measure this metallicity very, very precisely. So that means we can distinguish stars with different metallicities. Stars that were born just after the Big Bang, compared to stars that are like the sun at the present day. So going back to this kind of picture of the history of the universe, we've got the first stars on the left, we've got the Milky Way on the right. And a very useful thing about stars is that they form from gas that is enriched with metals by previous stellar generations. And then after they're formed, they do not change their surface over time. So no matter what's happening in the cores of these stars, the surface usually stays the same. So that means that the surface is kind of like an archaeological probe that we can use to figure out what the chemical composition was like in the early universe. And that tells us a lot about the history. So if a star is formed at this early time, say a few 100 million years after the Big Bang, it will be metal poor because there haven't been enough generations of stars to enrich the universe significantly. And then if a star is born later, it will be metal rich. And then in the Milky Way, at the present day, we actually have a mix of metal rich and metal poor stars. So that means that our Milky Way is a really good time machine to go back in time at different generations, just generations of stars. So then how do we actually do this? Is we take spectroscopic observations of stars. So we split the light of stars in the color of the different colors of the rainbow. And what you can start to see is that there's these lines appearing in the spectrum. And these correspond to signatures of specific elements. So for example, there's two strong features from calcium. So this star, which is the sun, has calcium, it has iron, magnesium, all the different elements, and everything that you can see here is the result of absorption from a specific element. And we can use the strength of these features to learn how much iron there is in the sun and in other stars. So usually we don't look at the spectrum in colors, but in wavelength. So wavelength is the same thing as color, but quantified as a number. So this is, for example, the same spectrum of the sun. And what you can see, all these wiggles here, they're all actual features. This is not noise in the data. This is all giving us information about the composition of the sun. So the sun is a relatively star rich in metals. So what would a spectrum of a metal poor star look like? And it is shown here in the black line. So the sun is again in gray, and you can see all of these different features. But then there's one of the most metal poor stars that we know is shown here in black. And you can see the only lines are here, which is actually hydrogen. And we know all stars have hydrogen. The only other line you can see is over here, which turns out to be a calcium line. So we use this difference that we can get from the spectrum to classify how many metals does a star have, and therefore likely how old is it to be. And we use this because it's really difficult to measure the ages of stars directly, whereas it's easier to get the composition of stars. So then we know how to recognize these stars, but how do we actually find them? These stars are quite rare. And as I was saying earlier, for example, this biggest catalog of stars in the Milky Way from the Gaia mission has around 1.8 billion stars in it. And what we need is some way to pick up these very rare old stars between all of these in this big set of data. So the point is that it's quite expensive in terms of time and telescope time, and you need big telescopes to get the spectra. So you can't just take spectra of all of these 2 billion stars. If you want to find the oldest stars, you have to do some kind of pre-selection to identify these stars. So here's again this comparison of these two spectra, the metal poor star in black, the old star, and then the sun in gray. And as I mentioned before, there's almost nothing in the spectrum except in this region. So this is the region that we often use if we cannot take an entire spectrum, we will focus on this region to identify metal poor stars. So as I mentioned, the spectroscopy is resource intensive, and these stars are very rare. So how do we approach this problem? In fact, we're using imaging rather than spectroscopy. So you're probably all very familiar with taking astronomical observations through different color filters, and these are broadband filters that are used very often. And in the project that I'm involved in, we're using a very narrow filter that I've highlighted here in black, that is just covering these two calcium lines that we saw earlier over here. So we're using a really narrow band filter to only get the light in this region of the calcium H and K lines. So here is a zoom in on that region. The white curve is the region where we're getting the light. And this is a simulated spectrum of a star of the metallicity of the sun. So you can see these very broad features. And then this is a star that is metal poor. So you can see that these lines are getting narrower. And then a very metal poor star, and then an extremely metal poor star. And as you go to lower and lower metallicity, and this is a logarithmic scale, so you're really, really reducing the number of metals in these stars. And this means that there's a different amount of light that comes through the filter. So a metal poor star will look bright, and a metal rich star will look faint because there's not enough light coming. There's not enough light left. So that's how we can use imaging. We just take a picture in this very narrow wavelength range, and then we pick up the stars that we think might be metal poor. And then we follow those up with more expensive observations. So this project is called the Pristine Survey, because we're looking for these pristine stars that haven't been polluted with heavier elements. And it's a sky survey of images in this calcium region, so this very narrow filter. And the filter is on this telescope, the Canada France Hawaii telescope on Hawaii, which is a 4-meter diameter mirror. So it's collecting a lot of light. And you need a big telescope to be able to do this. It's a decent sized collaboration. So a lot of astronomy is not done in isolation. We do it in collaboration. This was we have regular meetings online because we're spread across the world. But this is from COVID times where we all had to meet online, and this was our big annual meeting. And then sometimes we get to meet in person and discuss, share ideas, and work together on the data that we have collected. So then again, we now know what old stars look like. They're metal poor. We know how to find them. But then we also need to know where to look on the sky. So we know from galaxy formation scenarios and also from observations that the disk part of the Milky Way is the younger part. So this is where the relatively young stars are. And the galactic halo, which is this fluffy component that is surrounding it, is kind of like a sphere, like a big ball. Those are the older stars. It's the older component. So the best strategy to find these old stars is to look out of the disk into the galactic halo. And this is in fact what we've done with the Pristine Survey and what other projects are also doing. So this is again in the background a map of Gaia sources, so stars in the Milky Way. And in yellow, I've highlighted here the region that we're surveying with this project, this Pristine project. So we're still ongoing, so that's why there's gaps in this colored region. And you can see that we're staying away from the disk, which is here in the center of the image. So we're looking towards the halo out of the younger region. And we're missing actually this part of the sky, and that's because we are in the northern hemisphere. So we cannot reach the southern hemisphere with the telescope that we are using. So you might have noticed that there's also a part of this footprint that is completely different from the rest, and it's looking straight at the center of the Milky Way. And I'll say a bit more about that in a second. So in this project, we've already published many different papers on many different topics, all connected to old stars. So if you're interested in what the project is doing, you can have a look at our website. You can just Google the Pristine survey. So the project that was mentioned in my introduction was the Pristine Inner Galaxy Survey, or PIGS. So this is a project that I started during my PhD and have been working with since then. And the goal is to look for these old stars in the very, very center of the Milky Way. And this is a very challenging region because we are looking through the disk. If you remember, we're quite a while away from the center. So we're looking through the disk. There's a lot of dust that's blocking the light, that's changing the colors in unexpected ways. But we actually expect that the very, very oldest stars in the Milky Way are in its center because of the way that galaxies grow from the inside out. So that's why we started the project, looking at the very center. And there have also been various publications from this project as well. So this is one of the main surveys that's looking for these old stars. But there's also many other people doing complementary things. And in the last part of the talk, I just want to highlight what we have learned so far about ancient stars, the early Milky Way, and the formation of the Milky Way. So these are some relatively recent highlights. So I was speaking about the Gaia mission before already. So here's just a little bit more about the Gaia mission. So some basic information we want to know about stars is, first of all, where are they on the sky? We want to know very precisely where they are. How far away are they? How are they moving? And what's their brightness and their color? And the Gaia mission is providing this for almost 2 billion stars. So here's a little video of the Gaia mission is spinning. It's at the Lagrange point 2, so it's not going around the Earth, but it's further away and going around the sun by itself. And it's scanning the sky. So it's rotating, and in that process, it's scanning the sky every time. And it's measuring the positions of stars multiple times over the course of many years. And if you have the positions precisely enough, you can see how the stars are moving over the course of these multiple observations. And this gives you the distance and the movement of the stars. So that is that can then be used to reconstruct a 3D picture of the Milky Way, and also a picture, a dynamical picture, not just static. We can actually see how is the Milky Way alive, how is it moving. And I want to highlight two results that have come from the Gaia mission combined with other projects as well, that have been really kind of changing our picture about the Milky Way. So the first one is the contributors to the galactic halo, this fluffy component, and then the very old heart of the Milky Way, which is where my research also has focused. So first on the galactic halo. So here we have again this cartoon image of the Milky Way. We have the disk that has 99% of the stars, and then this fluffy component that really contains a lot of information about the early history of our galaxy. So in this picture of hierarchical galaxy formation, where you get the small things merging into bigger things and bigger things over time, you would expect a lot of the stuff that comes in later, the small things, to be ending up in this fluffy component. And those are the kind of building blocks of the galactic halo that we can try to start picking up. So how do we recognize it? If we look at the galactic halo, are all the stars just smoothly distributed? Are they all moving randomly? We've actually found that this is not the case. There is clusters of stars that are moving together. And this is a picture. In the background is again the Gaia map. And overlaid is stars that are all spatially together, that they're all at the same distance. That is the color scale. And then they're all found out that they are moving together in terms of their velocities are all similar. So we call these stellar streams. And these stellar streams are the remnants of objects that are in the Milky Way that are being disrupted by the Milky Way itself, because they're going around and they're being stretched, and at some point they will dissolve completely. So this is from a search in the big 2 billion Gaia catalog, looking for stars that are moving similar. And they found all of these different streams that are going all throughout the Milky Way and that are being disrupted. So we found out that many of these are probably originating from globular clusters. So here's a nice picture of a globular cluster that we think this stream belongs to. So globular clusters are groups of thousands of stars together. They're very, very closely packed together. And you can see many with even with small telescopes. So a lot of these are surviving and we can still see them, but it turns out that there's a lot of them also that are currently being disrupted. And in the past, there must have been even more that are now not coherent anymore. So these disrupting globular clusters are contributors to this fluffy component of the Milky Way. But it turns out that they're actually only a very small contribution to the galactic halo. It's a very small fraction. And it turns out that the mergers of small galaxies are contributing a lot more to the Milky Way. So we call these smaller galaxies dwarf galaxies, just because they're quite a bit smaller than the Milky Way. And they can also produce these kind of streams, but much, much bigger than these globular cluster streams. So for example, this is an artist impression of the Sagittarius stream. So this is a large dwarf galaxy. We can still see the core of the galaxy that is currently disrupting into the Milky Way halo. And it is contributing a lot of the stars in that region. So this was discovered by Cambridge astronomers in around 30 years ago now, and has caused a lot of study since then. So this is one of the major components of the galactic halo. And then more recently, we found out that there is a much longer ago, there was a galaxy that merged with the Milky Way. It's been given the unfortunate name of the Gaia sausage Enceladus. It was discovered by two groups separately. One group in the Netherlands who called it Gaia Enceladus, and then one group here in Cambridge who called it the Gaia sausage. And since it was around the same time, we now call it the combined name, or for short, GSE. And this one was found through velocities of stars that were all moving together in the Gaia data. And here's a little simulation. So someone tried reconstructing this process. So in blue is the Milky Way and red is this system. And you can see that it's causing disruption to the Milky Way, but also the system is getting completely disrupted in the process. So it's no longer a group of stars together like a dwarf galaxy, but it's spread all over the Milky Way. But even though they're not spatially together anymore, we can still recognize it that they're moving in the same way. So we can find out that they are actually originating in the same system. And I don't have time to go into it today, but they also have different chemical properties in terms of their the composition. So this turns out that it's actually probably almost half of the galactic halo is made by this system, and the rest is just a lot of smaller system, maybe some stuff that was originally already in the Milky Way. So here is for those who are interested in a little bit more detail, but don't worry if this is as a bit too much. We can look at the angular momentum of stars and compare it to the energy. That means how tightly they're bound to the Milky Way. And then we can actually find many different groups. So here they're color-coded by, we think that they all come from a different dwarf galaxy. So this is a mix. The halo is really a melting pot of different structures. And if you show it with the same colors on the right-hand side, this is the distance from the galactic center. So if you're close to the center, you have a different mix compared to when you're far away from the center. So you have Gaia, Sausage, and Enceladus is kind of dominating over here. And then as you go further out, it's this Sagittarius stream. And then it turns out there's also a lot of different other small things. And then there's stuff we haven't classified yet. We don't know where it comes from. So this is still a very active area of research. And people are sometimes even fighting over whether they found the same thing. It's been given a different name. So yeah, it's a very active topic to dissect the halo of the Milky Way and kind of reconstruct which kind of small things came into the Milky Way. So the second highlight I want to talk about is what some people have called the poor old heart of the Milky Way, or the very central old region of our galaxy. So that is this kind of region where you also have the disk being thickened. So there's an overlap between the highest density part of the galactic halo that's in the center and the thick part of the disk in the center. So there's a lot of things happening, and you really need to be able to do well at finding these old stars. So if you look at simulations from galaxies, then you can see that here is kind of the distance in two different axes. And the darker the color, the higher the density of really old stars. So you can see that in the very center is actually where you expect a lot of these old stars to be, kind of lying in the middle between the other stars. So here's again the beautiful map from Gaia. And you can see that this is color-coded based on the blue and the red colors of the stars. But there's actually a lot more information in the Gaia data where you can actually, based on the very detailed colors, you can predict the metallicities of stars. So you can find the population of old stars. And if you do that, you can show them on the sky in a similar way. And this is from a recent publication. It's all of the bright metal poor stars in the latest Gaia release. And you can see they're kind of showing this round distribution, a very high density in the center, and then it becomes less and less as you go further out, compared to here the disk, which has the highest density in the plane. So this is very nice, and this is what some have called the poor old heart of the Milky Way. This is really, we think, the first billion years of the Milky Way is where these stars came from. And this is where my project comes in as well, this pristine inner galaxy survey. We look at the center to exactly find this old component. And if you remember, the strategy of the Pristine project was to use this very narrow band imaging to identify these old stars. And it turns out that works really well. So here on this axis is younger stars on the right and older stars on the left. And kind of normal surveys, if you randomly select stars in the inner region, you get a distribution somewhere like this, so kind of biased towards the younger stars. And then in the PIGS project, we've only selected those promising old ones. And in fact, once we measure the metallicity, we get completely different distributions. So for the first time, we really get a new set of glasses on the old galaxy. So one highlight that I published very recently is on how these old stars move. So we found them. They're currently present in the inner regions. Are they moving like the disk? Are they going in circles around the galactic center? Or are they more on random orbits? So the sun is moving like this in the Milky Way. It's going roughly in a circle around the center, roughly always the same distance from the center. And it's just going round, and it's not really going out of the disk. You remember this thin plane is always staying in that thin plane. So in PIGS, what we actually find is more something like these cartoon orange stars. So these stars are very elliptical orbits. They can go on all kinds of different angles. And this is really what we expect for the kind of a halo component. So they're not circular, they're elliptical. They're mostly at random orientations with respect to the disk. It's almost as if they don't care that there is a disk in the Milky Way. And they're mostly staying in the very inner regions. So they don't really make it out all the way to the sun. So you really need to look towards the center to find them. So this is something new that we hadn't observed before. It was predicted, but we hadn't been able to see it. And we also found evidence for the presence of two separate components among these very old stars. And we interpret that as one, these small disrupted galaxies that came in over the course of the history of the Milky Way that have made a floppy component. But we also find another one that we think is connected to something we've only been recently really investigating, and that is the population that formed inside our own Milky Way in the very first few 100 million years. So when they formed, here on the left, this is again a spatial distribution. Let's say if you would look at it on the sky, it's very clumpy. These stars are forming in clumps. But at the present day, these stars are distributed like a sphere. They're just kind of round. And this is what we think we're seeing, the very baby phase of the Milky Way. So to summarize the talk, we've started with the question, how did the Milky Way form? And in general, how do galaxies form? And this is this hierarchical picture from smaller to bigger galaxies like the Milky Way. And we can find traces of some of these individual events that ended up in the Milky Way. And how we can do this is we use these very small stars that can survive for a long time, and we look at their spectra. And we can see all of the different elements in there that are making up this very tiny wedge compared to hydrogen and helium, but that is the bit that really holds all of the information. And then in the second half, I gave a couple of highlights especially from the Gaia mission. So looking at the accretion events that happened in the Milky Way, and then also looking at the very old heart of the Milky Way. Thanks, that's everything I wanted to share.
Thank you very much. Can I ask everybody to join with me and give you a quick round of applause? That was a fascinating talk. Thank you very much, Anke. Could you stop sharing your screen for the moment?
Yeah.
And we'll go back to our gallery view where we can see all the usual suspects. And ladies and gentlemen, it's question and hopefully some answer time. And I've got a few questions, but anybody in the room? We'll start off with Tony Morris.
Hi, thank you very much for the talk. Really interesting. When you were talking about metal poor stars, you were using the metal calcium to help you detect them. Where does the calcium come from?
Yes, so we're using the calcium as a proxy for the overall metallicity. It turns out it correlates relatively well with all of the different elements as well. So I could briefly share the screen again and go back to the periodic table. Where is it? Here. So calcium is shown here. So it's mostly a mix of exploding massive stars and exploding white dwarfs that creates calcium. So we're not observing the very first generation of stars. That's only hydrogen and helium. I forgot to mention that, but the very first stars, we think that they were really massive because they couldn't form smaller stars because of the lack of heavier elements. So these stars exploded very quickly. So that means they enriched the universe with some elements. So all of the stars that we see at the present day have at least a little bit of elements. So they're the second generation or later.
Okay, yeah. Thank you. Okay, I forgot to say to our online guests, put a digital hand up if you have a question, and I'll bring you into the conversation. Gary?
Yes, thank you. Great talk, Anke. Brilliant. Thank you very much for that. About your metal poor stars that seem to aggregate more towards the centre of the Milky Way, do we think that this is a product of the fact that we find more of them at the centre of the Milky Way, because the outer arms may act as a protective hoover for any collisions or anything creating any further disturbance in the inner core of the Milky Way? And the second question is, when you showed us that there was an ellipses of the metal core stars rather than is that because they are less dense objects, and so therefore they may not have such gravitational pull by the Milky Way? And just two conjectures there that I'd like you to kind of think on. And
Thanks for those questions. So we think that this component in the inner regions formed before the disk did. So we first have this kind of chaotic component that is old and metal poor, and then at some point, we don't really know yet exactly what causes it, the disk of the Milky Way starts to form, and you get younger stars forming. So it's kind of a sequential thing in that sense. It's not that the disk is protecting or doing much to these stars. It's just that they formed at a different time. And then we do get these events coming in now still, but they just get disrupted and give their stars in this kind of spheroidal component. And the stars that are in the disk are mostly the ones that are forming inside the Milky Way. And your second question was
about the elliptical orbits of the metal core.
Right. Yeah, so that's connected to the answer for the first part. So we think that the very early formation was quite chaotic and didn't necessarily happen in a disk, or if it did, the disk would get destroyed and disrupted. And it's easier so if that happens, the stars kind of just get distributed more randomly. And then later, when you start forming a disk, you also start forming these stars in these circular orbits, because they form where the gas is, and the gas goes into a disk. So it's connected to the formation processes of these where they formed.
Okay, Greg Bagnett.
Hey, thank you. Yeah, that was interesting talk. Very interesting. Thank you. I'm curious about the globular clusters. They are part of the oldest collection of stars. I'm just curious, were they involved in the formation of the Milky Way, or what's the relationship between the birth of the Milky Way and the globular clusters? It seems like that they have very little metals, that they would have been almost there at the beginning. Just trying to understand that.
Yeah, no, that's exactly correct. So we think that maybe around half of the globular clusters formed inside the Milky Way, and the other half formed in the systems that were accreted later on. So the stars that the globular clusters we can kind of tell from the way they're moving and from their chemistry which ones came in later with dwarf galaxies like this GSC system, and which ones were born in the Milky Way. And yeah, they are very old, these globular clusters. So we think they must be from the same phase as these metal poor stars that we find just in the field.
Got it. And just a follow-up question, is it a 1-for-1 correlation between the amount of metals in the stars or the clusters and their age? I mean, is that a very accurate way of, I guess, figuring out how old they are, the level of heavy metals or elements they have?
Unfortunately, there's no 1-to-1 correlation. So it's a relative age scale that we're using. And again, it depends on the environment that they formed in. So for example, the age metallicity relationship in the dwarf galaxies is different than in the main Milky Way component, which is actually something we can use to disentangle where stars formed, if you can get ages for the stars.
Got it. Thank you very much.
Okay, thanks, Greg. Roy Dodson in the room.
Yeah, I'm just wondering, these early stars, metal core stars that orbit towards the centre of the galaxy. Is there any correlation between them? My understanding is globular clusters are very old stars and metal core stars as well. So is there any correlation between the stars in globular clusters and these stars within the galaxy that you're talking about?
Yes, yeah, we definitely think that there is. So these different streams that I showed on the sky, this map of all these different colored streams, we think those are all disrupting globular clusters. So that means that they used to be these balls and now they're kind of being stretched. And if you would wind the time into the future for a few billion years, they would be completely disrupted and they would start contributing to kind of this field population that we see in the halo. And we actually think this is also something that we've just been finding out of the last 5 or 10 years, that a lot of these globular clusters were probably disrupted very early on in this early formation phase of the Milky Way. It's probably very chaotic. So we think that the fraction of stars that comes from globular clusters is actually larger in the center compared to the outer parts of the galactic halo.
Okay. Okay. Graham.
Am I right in thinking that these disrupted structures, which have the very elliptic orbit, the plane of the orbit is going to be stable? It isn't going to converge with the disk. It's going to, it'll become more disrupted and spread around the ellipse, but it'll stay in the same plane relative to the disk. Is that it?
So as far as I understand correctly, you're saying that these stars will not end up in the disk, right?
Yes,
They're kind of going to end up in the halo.
Is that the current idea, that they will remain in this, the orbit will remain in the same plane, whatever it is, in relation to this?
Roughly, it's if you go long enough, then they won't actually stay coherent, because there's like heating effects from the fact that it's moving around, might be moving through the disk, and at some point these stars are losing their coherence. So we think that for depending on how long ago this disruption happens, you can still kind of piece it together, which stars belong to the same thing. But if you wait long enough, then this coherency will get lost.
Okay, great. Celeste Ellis from Texas. Welcome, Celeste, or Celeste. You had a question on the chat. Would you like to ask it?
Yes, as far as after the Big Bang and everything started happening, at what point and how did gravity begin?
I wasn't really sure myself.
So that's a very good question, and it's a question for maybe a theoretical physicist. So we think that gravity started very, very, very early on. So almost before anything else happened. But there is a phase where all of the forces, so there's 4 fundamental forces where they were all connected to each other. And this is maybe, a few billionth of a second after the Big Bang, where they start to decouple and become individual forces. And from that moment on, gravity acts and actually kind of rules the universe.
Okay, Celeste.
Yes, thank you.
Thank you very much. I'm looking around the room for any more questions. Tony Morris wants to come back. If you've got a question online, don't forget to put a digital hand up. Tony?
I was thinking about the very first generation of stars with no metals. Have you detected any of those?
No, we haven't.
So,
No,
is that for James Webb Telescope to look back for those stars?
Yeah, so that the galactic archaeology technique probably doesn't work for these stars because they were likely very massive and they wouldn't survive until today. So we wouldn't see them if we, look around us. But it's a very big part of the science program, I think, of the James Webb Space Telescope to try to see if if they can actually see them at the very distant universe, so the high redshift in these young galaxies. But the problem is again that you're looking so far away, so you only get a little bit of resolution. You cannot resolve individual stars. You just get the combined light of a galaxy. So people are trying to figure out how they could show or prove that, you know, these stars may contain some of these metal-free stars, but so far nothing convincing has been found. Yeah.
Okay.
So I think one other way that people are hoping it, maybe not seeing the stars themselves, but seeing their explosions. So if these stars explode, they might have a unique signature, and they'll be a lot brighter than when they're just living their life. But this is again something that we haven't found yet.
Okay. I'm making one last look around the room. I can't see anybody with a hand up. I've got nobody on with a hand up online. Ladies and gentlemen, can you join with me by giving a huge Mexican Swinton astronomy society thank you to Anke for an absolutely fascinating talk. Thank you very much.
Yeah, and thank you for all the good questions.